All right, good day, everyone. So now we're going to look at a problem relating to the diesel cycle. It says here an oil engine works on the ideal diesel cycle. The overall compression ratio is 11:1, and constant pressure energy addition ceases at 10% of the stroke. All right, so that's when the diesel is entering the cylinder, okay, when it's getting injected in at constant pressure. Intake conditions are 96 kPa and 18 degrees Celsius, and the engine uses 0.05 meters cubed of air per second. And it says, or per stroke, per stroke. If gamma equals 1.4, determine the thermal efficiency of the engine and the indicated power of the engine. Remember, the indicated power of the engine is the actual work done inside the cylinder as that gas expands, okay, and from the heat addition. All right, so let's see what's going on here. So first of all, before we begin, you have to draw the pressure volume diagram. It's very important that you do this so you know what you know the different gas processes that are happening. All right, so here at the beginning of the compression stroke, position 1, what I've done is I've put the compression ratio on the volume line, okay? So you can see here when the piston is all the way at bottom dead center, I've put 11, and when it's compressed that gas to 0.2, you can see I've put 1 there. All right, so 11 is to 1. All right, but we don't know what the actual volumes are yet. Then that's what we're going to work out later. Okay, but then they do give us the information though that the engine uses 0.05 meters cubed per stroke. All right, so they give us that. And let's see what else. Okay, so how do we start? So the swept volume. Okay, so this is the swept volume from 0.1 to 0.2. That's the swept volume, right? And they told us that the compression ratio is 11:1. So how many volumes is it from 0.1 to 0.2? Okay, so if over here from 0 to 1 is 11, right? And from 0 to 0.2 is 1, how many volumes is this? And that's very easy. That'll just be 10. So like I wrote here, one volume plus 10 volumes equals 11. All right. So the swept volume is 10 volumes from 0.1 to 0.2. All right. Then it says that 10% of that swept volume is when heat is added into the system, right? So heat is added at constant pressure, right? So this is when the diesel is injected, and that's over there, right? So what is 10% or 0.1 of 10 volumes? And that'll be just 1 volume. So like I wrote here, 10, which is these 10 volumes, times 10% gives you the volume from 0.2 to 0.3. All right, so and that's where the constant pressure heat addition is. Okay, so I'll draw here my arrows to show that my heat is being added there. All right, so now we got that done. Now we can work out the thermal efficiency of this engine. All right, so the nice thing is that we get this formula on the formula sheet, so we don't have to derive this. And here it is. So on page 3, you have the thermal efficiency relating to the diesel cycle. Okay, so how does this formula work? So we have to know, we know what gamma is, but we have to know what beta and what R equals. All right, so if we look here I've written down the formula from the formula sheet, and R is the compression ratio between 0.1 and 0.2. Okay, so that's the compression stroke. So that is V1 over V2. And still at this point, we don't know what that volumes are, what those volumes are, but we do know what the compression ratio is. So the at point 1, it's 11, and at point 2, it's 1, right? So that's very simple. So to calculate R, we're just going to say V1 over V2, so it's 11 over 1, and that is 11. Okay, so they've given us that actually in the question, the compression ratio. And then beta is where the constant pressure heat addition takes place. All right, so over here, that's between 0.2 and 0.3. So we need to know that. So beta is just V3 over V2. All right, so we know what V2 is. V2 is one volume. And now what is V3? Okay, so V3, how we get that is, we were told that the constant pressure heat addition was for 10% of the stroke. Okay, so if we know that the stroke is 10 volumes, okay, that we just worked out earlier, the stroke is 10 volumes because the compression ratio is 1 is to 11. So this is 10 volumes. So what is 10% of 1? 10% of 1 is just 1, right? So that means that from 0.2 to 0.3, when the constant pressure heat addition is taking place, that takes place for one volume, one of these 10 volumes, okay? So because it says 10% of the stroke, so that's one volume. So very easy then. So beta is V3 over V2, and we know now that what is V3? V3 is one volume plus another volume, so that's two volumes, and V2 is just one volume. All right, so it's 2 over 1. So there I have it there. V3 over V2 is 2 over 1, and beta equals 2. And then it's very easy to get the thermal efficiency with this formula, because now we have everything. So we have beta, we have R, and we have gamma, which is 1.4. So we just plug everything in, and I'll let you do the math, and the answer comes out to 55%. Right, so that's for the thermal efficiency of this engine. Okay, so the next part now is the indicated power of the engine, right? So now we're gonna have to do a bit of simple calculations to figure out the volumes and the pressures. Okay, so let's start. So over here, let me just get this into camera here. V1 to V2, I said is 0.05 meters cubed per stroke. Now they gave us that in the question, right? Now, so that means that they are saying here that the intake conditions, okay, they gave us the pressure of the intake conditions. So we know what the intake pressure is now at 0.1. So they said that's 96 kPa. And then they said the engine draws in 0.05 meters cubed per stroke. Okay, so that's what it sucks in. Okay, so therefore we know how much air is going to be pulled into the stroke, or the volume that will be pulled in between 0.1 and 0.2. Okay, but that still doesn't give us what the volume is here, and it doesn't give us what the volume is over here. How do we get that? So what we need to know is, so that 0.05, that's for 10 volumes, all right? So that's for 10 volumes. So if that's for 10 volumes, how much is V2? And what we do is we take 0.05, which is the amount that the cylinder pulls in of air, and we're going to times that by 0.1, right? Because we know that if that 0.05 is for 10 volumes, how much is it for just one volume, for V2? And all we need to do is we say 0.05 times 10%, or times 0.1, and then it'll give us the volume at 0.2. Okay, so that's what I've done here. V2 equals 0.05, again the amount that the cylinder pulls in, times point 0.1, and we get 0,005 meters cubed per stroke. Okay, so that's for one volume. Okay, so at this point here, it's 0,005 meters cubed per stroke. Now, how will we get what V1 is now? It's very simple. It's going to be this volume plus what it pulls in. And then we'll know what the volume at 0.1 is. Okay, so there's two ways you can do this. You can say V1 equals 11, because that's the compression ratio, times 0,005, which is, this is V2. And then you'll get 0,055 meters cubed. Or you can just say what it pulls in from the cylinder, which is between V1 and V2, plus V2, and then you get, so it's 0,05 plus 0,005, and you get what V1 is, which is 0,055 meters cubed per stroke. All right, so that's quite easy as well. Now, how do we get what V3's volume is? V3's volume, so we know what V2 is, and we know from earlier on that this was one volume, and constant pressure heat addition was also for one volume, or 10% of the stroke, so which we calculated to be another volume. So V3 is just two volumes. See, two volumes. So all we do is we basically just say V3 equals 2 times V2, and we get 2 times 0,005, and that is 0,01 meters cubed. So now we have V3. And what about V4? V4, super easy, because the volume at 0.4 is the same as the volume at 0.1. So we have that as the same as volume 1, which was 0,055 meters cubed. All right, so that's that. Now the pressures. Okay, so we got the inlet pressure, they told us, at 96 kPa, and they even told us the temperature, which was 18 degrees Celsius. So we know what the inlet conditions are. So we know the volumes and the pressure and the temperature at 0.1. So now we need to find out what the pressure is at 0.2. Okay, so we need to know this pressure. And we've already calculated the volume at 0.2. So that's helpful. And we know that this process, they told us, you can see it here, it's an adiabatic isentropic reversible process because of 1.4. So we can use on our formula sheet, and actually it's on the question itself, we can use here PV to the power of gamma equals C. All right, so that's on page 1 of the formula sheet. So we're going to use that to calculate the pressure at 0.2. So there, I've got it there. P1 V1 to the power of gamma equals P2 V2 to the power of gamma. And we substitute the values in. Remember, again, we can use the compression ratio here because it's a lot easier just to put 11 in there. And then we can get P2. Then the same for the second, for the expansion, I should say. For the expansion, it's the same formula to get P4. Just take note here that V3 is, remember how many volumes that was? It was 2 volumes. And because you can see here, V2 is 1 volume, V3 is another volume. Remember 10% of heat addition. So that's 2 volumes. So now you have to have V3 over V4. So that's 2 over 11. And remember V4, we know what that is because it's the same volume as V1. So that's 11. And then we can get what P4 is. Okay, so that's very easy to do. Now the last part is, now that we've got all the volumes and the pressures, now we can calculate what the indicated power is on this engine, right? So how do we do that? Okay, now I've got this big formula here, and they show you where they get it on page 102. Okay, over here, page 102. All right, and they show you how they get this big formula, but I'm not going to look at that. It's actually you should just go read through that, but it's actually very easy. It's on your formula sheet actually. So remember, for work done on, okay, so go to page 2 on the formula sheet. So for work done, it's the area under the pressure volume graph, or the curve, or whatever process is on that graph. All right, and there we have the work done there. All right, and then also I've given it to you on this gas processes sheet. All right, so you can see over here at the top here, the work done over here under these processes. It's the area under those curves. All right, so over here for a constant pressure process, it's P times change in V, because that's the area underneath this graph. And for the adiabatic process, it's P1 V1 minus P2 V2 over gamma minus R. Well, sorry, gamma minus 1. All right, so that's the area under that curve. Okay, so those are actually the two formulas that we're going to be using for work done. And again, it's on the formula sheet there. That's for a isobaric or constant pressure process, and over here polytropic, and here is for the adiabatic process because it has gamma. All right, so there's the curves, or there's the formulas. Okay, but now we need to combine these, because we don't just have a adiabatic process. We've got two adiabatic processes and one constant volume process. So if you look here again, so that is an adiabatic compression. We have an adiabatic expansion, and then we have a isobaric or constant pressure process over there. Okay, now we can't just say this area underneath here, underneath this line. If you follow this line from 2 to 3 to 4, you can't just say that is the work done, that's the work out, but you also have to subtract the work in. Okay, and that, where's work in? It's the compression, right, from point 1 to point 4. So basically we have to say from point 2 to point 3 to point 4, that whole area minus the area from point 1 to point 2. So it's this area here. Okay, and what I've done is, you can see here, I've done this. I hope you can see that. But you can see they overlap each other. So the orange, that's point 2 to 3 to 4. That's this whole section, right? And then so that's your work out, and your work in, it's just the green section there. Okay, so you have to work out this whole work out minus this work in, and you'll have the work, or the indicated work done, right? So that's the engine inside the cylinder, the power inside that cylinder. And you can see here, there's the formula. So this part here is for the constant pressure process, the isobaric, and over here is a combination for the two adiabatic processes. Okay, so P3 V3 minus P4 V4, that's this expansion process over there, the expansion process, and P2 V2 minus P1 V1, that's for the compression process. Okay, so that's all it is. And then once you've done that, so you're gonna have to remember, that's why it's important to draw the graph, so that you can get this formula, which they don't give it to you in this form, but they give you the individual processes on the formula sheet. Then you can put this formula down, and you can calculate what the indicated power is. All right, so yeah, so I hope that helps, and yeah, I'll see you in the next video.